All right, good afternoon, everyone. My name is Jim Haney with the RIT Launch Initiative. I think we have sorted out all of our technical difficulties, and hopefully now everyone will be able to join us for a live DFMA training session. I'm just going to wait for a response from the chat to make sure that everything is functioning properly. All right, looks like we're all set, so let's get started. To begin, if you're not familiar with DFMA, I would suggest watching the multi-part video lecture series that the team has put together. It can be found in the playlist section of the team's channel. Today, we're going to do an interesting exercise in DFMA that I would recommend that anyone who does any design work goes through periodically. What we're going to do is take one of my designs from about a year and a half ago, go through how I designed it, and how it would apply to my current knowledge of DFMA. Since you're always learning and experiencing new techniques with DFMA, it's a good idea to go back periodically and look at your old designs to see how you've changed as a designer. I like to do it every 9 to 16 months for most of my projects. So today we're going to be looking at my Level 2 rocket, Lightwave 1. We're going to go over the design methodologies I used in the past and what I would change if I was going to remake this rocket today. So to start with, let's do a quick review of what this rocket is. Lightwave 1 was a single deploy Level 2 rocket that would fly to 12,000 feet to test out new experimental live stream camera systems for the team. Since the live stream cameras are the main focus of this rocket, there is a very large avionics bay in the center that there was a lot of design practices that had to go into getting it to work properly. So if we go back to the section analysis view, let's work through each section of the rocket one at a time, starting with the nose cone. So the nose cone itself is not something that I designed. This was a part that was just off the shelf, and I only had to replicate it here in Fusion. If you didn't know, you can export nose cone geometry as a PDF or SVG from OpenRocket to then import into Fusion. That's why you could see this nose cone is made up of a series of small interconnected straight lines revolved around a central axis. This is not ideal for actual manufacturing. If you were to actually manufacture, you'd want to do a fit point spline along all these points in the imported SVG. But as a visual representation and for renders and animations, it's more than good enough. So let's go ahead and hide that nose cone. Inside the nose cone, I had a bulkhead and an eye bolt and an eye nut. This is a common attachment practice. You'll see this in pretty much every rocket's nose cone that doesn't have a solid sealed bottom. This technique, though, of just putting a floating bulkhead in is a lot harder than CAD makes it out to be. If we turn back on the nose cone and the section analysis, you can see there's not much actually stopping this bulkhead from moving backwards in the nose cone. So when I went to glue this up, if the fit and dimension wasn't perfect, what ended up happening is this bulkhead would either sink back another few inches into the nose cone until it started to hit the taper, or it would sort of bend and deflect and it wouldn't be straight up and down, which can lead to unequal loading during deployment forces. So if I was to remake this, I would probably make this a much thicker part, maybe out of a 3D printed material, that gives me a much larger cross section so it's less likely to bend or bow. I'd also like to potentially add some sort of identifying edge on it. So maybe in the future I would move this entire bulkhead up 4 to 5 inches into the nose cone so that I can use the natural taper of the nose cone to locate that bulkhead. The other downside of this design is that I permanently glued this bulkhead in place, so I'm not able to put any counterweights or future payloads inside of the nose cone if I wanted to. The eye bolt and the eye bolt and the nut, which is not modeled here, are just commercial off the shelf. There's nothing really special or interesting about those. One thing I would maybe change, not about the design itself, but how I would assemble it, is I would attach the eye bolt and nut to the bulkhead and then secure that with epoxy before moving the entire bulkhead into place. I had just put them together with normal friction, how you would normally attach a bolt and nut before installing the bulkhead. So I had to essentially inject epoxy in and around the eye bolt to get it solidly secured. Again, if it was a removable bulkhead, that would have solved that issue as well. So now we can move on to the parachute bay. There's really not much to say about this. It's an off-the-shelf tube. It has 2 parachutes in it. From a manufacturing and assembly standpoint, it can't get much simpler than that, so I think we're all set there. Now let's move on to the Avionics Bay, which is by far the most complex and worst part of this rocket. This Avionics Bay was a charm-style bay, where all the avionics are contained inside of a coupler, which is translucent in this view. And there's a small strip of actual body tube around the center to locate the Avionics Bay. One thing you'll notice is that there's no connection mechanism to hold this to the parachute bay or to the booster below. I ended up just drilling 4 bolt holes through it at random once I put it all together, which in hindsight, now I don't know where exactly those holes are in CAD when I want to remake parts, and the holes are not at a perfect spacing, so I can't just rely on some pattern and rotate around them. In the future, I'd probably want to design and machine out those holes using something from CAD rather than just freehanding them. So to give you an example, now I don't know necessarily if something like this part of the avionics housing that comes very close to the coupler tube will fit, since in the real rocket there might be a bolt and a nut there. For retaining the bolts, I originally had just threaded them through the blue tube, but I found that actually 3D printing a block and then putting a nut in the back of that block works best. You can actually see an example of a similar design right here. So normally what you would do is just put a nut against the inside surface of the tube and then epoxy it there. The thing is, that doesn't get it to sit perfectly flat, so it's better to 3D print a small block like this that has the curve of the inside of the body tube or nose cone already made into it, and then just a recess that will hold the nut in place. This also gives you a better contact area when you're gluing down the part, and can make manufacturing and assembly a lot easier. So moving back to the Avionics Bay, currently it's configured for a payload of 4 Raspberry Pi cameras, one of which is live streaming over a 1-watt antenna. It also has a egg timer quark for its deployment, and we can't see it in this view, but there is also a egg timer tracker, or an egg finder, I believe it's called, and an egg timer Wi-Fi arming switch to turn on and off the Avionics Bay. These cameras and radio systems take a lot of power, and since the rocket would be flying so high and far, there was a concern over the batteries dying mid-flight or when they're just downrange and we'd lose our tracking. So you can see there's quite a few batteries in here. We have 2 very large 2S batteries and 1 traditional 18650 3.7 volt LiPo. Batteries are something a bit tricky with rocketry, because ideally 1 large battery will be better than multiple small batteries from a cost and density standpoint. The challenge is you can't really run everything off of 1 single battery. So for example, with this setup, I had the avionics and tracker running off of 1 2S battery and the transmitter for the video running off the other. If I had combined those both into 1 battery, there would be a concern that if the transmitter was drawing more power than expected, I wouldn't be able to actually find the rocket because it would completely drain all the power that should have been used for the tracker and radio system for telemetry. The downside also to multiple batteries is that they're a lot harder to place in three-dimensional space and take up a lot of space if you're using a traditional 2D sled for your Avionics Bay. I tried experimenting with a three-dimensional sled where parts are held in 3D space at different points with this Avionics Bay, but ultimately I wouldn't recommend it for something like this. Our first problem with this Avionics Bay, now that I've gone through the whole design process and tried to squeeze all these parts in there, is that this is way too much stuff. So if you look in CAD and you look around, it looks like everything fits nice and snug. You got plenty of gaps between parts, There's spacers, there's nothing touching the threaded rod, it's all great. The challenge is that you sort of lose a sense of scale when you're designing. So, these spacers, they look great and all, until you realize that they're only about a 0.5 millimeter. So now you're dealing with these very small parts, you have to go in there with tweezers, you have bolts that are insanely tiny, and getting dimensions for the bolt holes with a 3D printed floating sled like this is very difficult. So really the first thing we should have done is not had this many parts in there. And that sort of comes into the DFA aspect of this. You really need to know what parts you need for the mission and then design the rocket around it, or know the constraints of your rocket and then design the mission around that. For this size of Avionics Bay, since it's already built and I can't modify it, I would probably want to reduce the scope down from 4 cameras to 1, and maybe decrease the size of the transmitter for the video from 1 watt to 600 milliwatts. Cutting the power of the radio also significantly decreases the size and complexity of including the radio in the rocket. The downside, of course, is that we wouldn't have 360 video from this rocket, and the video feed would get cut off sooner, whereas this one might be able to survive up to apogee and then get a good amount of the descent. We might lose a 600 milliwatt about 5,000 to 7,000 feet up, and then regain it on the descent. If I wanted to focus on getting the 360 video and I didn't care about the live stream, taking out the antenna and radio transmitter and then replacing these Raspberry Pi cameras with a commercial off-the-shelf small camera like an SQ12 would also make this entire assembly a lot easier. The Pi cams, while they are fairly cheap, are extremely delicate. There's a very thin ribbon cable that can only be connected and disconnected a finite number of times between the camera module and the Pi. So if you need to modify things, move things around too much, you end up breaking stuff. It's better to use a self-contained module and pay the few extra dollars than have multiple broken systems. So I would start, if we were going to retool this rocket, by getting rid of the antenna. Let's turn off the analysis so we can see everything we're doing. So I'd get rid of that live stream antenna. It's just not worth it. We can't fit it in this rocket. Let's focus instead on getting that 360 video. The egg timer quark, we obviously need that. Can't get rid of that. This sled was designed to be 3D printed and would hold the top of the Pis, which we won't need anyway. But let's isolate that part and take a look at the design and what could be improved on that part if we wanted to use it again. So this part was to be 3D printed. What's good about it is I used the fact that there was a threaded rod running through the entire length of the Avionics Bay to retain this part of the sled by just securing a thread lock nut or a nylock nut in the center of this sled. I was able to constrain this piece in all 3 axes. The downside with constraining things on a threaded rod, especially when you have multiple components like this half of the sled and the other half of the sled, is that you need to be careful of the thread alignment, or you need to make all the parts be able to be located concentrically. In this case, this hole here, 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 all the way around needed to exactly match up with holes on the Pis, which are also retained by the lower sled. But since I didn't take into account the thread pitch and the distance between the nuts that would work properly, those holes never quite lined up, and I ended up having to shift this entire sled up and down on its nut. You could also get around this by just making a single piece sled and then having multiple nuts underneath it to support it. Yeah, so Matt in the chat just mentioned another challenge of the actual orientation of printing this part. This part was definitely not optimized for 3D printing. There's no great way to position it. So you obviously have this very thin feature here, perpendicular to another very thin feature here, perpendicular to a bunch of bolt holes that if they're printed anything except for straight up and down, you don't get an accurate size and your bolts won't fit. Something like this, if you needed to go for this approach, could probably be done easier in 2 to 3 parts. Whether that be maybe laser cutting this part, removing this part, and then printing the rest, or printing it in multiple parts and then all come together around the hex nut in the center. But for now, we're just going to get rid of that altogether. The SQ12s that I mentioned earlier, what's nice about them compared to the Pies is that they are a smaller cube that are easier to retain no matter where you are. So let's keep going and see what else is wrong with this. You notice some of these components, like the Raspberry Pis, are a lot more detailed than the Quark and the Egg Finder. Some components have commercially available or free-to-use CAD models that are very accurate, and this can help a lot with DFA. So you can see with these Raspberry Pis, I was able to design parts that come in very close to the connectors and the physical parts on the boards to ensure everything fits together properly. Now, of course, you need to worry about the accuracy and the dimensioning of these CAD models when you find them, but if they are available, it does make the DFA process a lot easier. The Quarks and the Egg Finders, on the other hand, don't have any commercially available dimensions or CAD models. Instead, you either need to design them yourself, which takes a lot of time, or use this bounding box or black box approach, where you just make a basic shape that would cover where this part would sit in general. You know, maybe there is some extra space in there, maybe it's not totally indicative of the final shape, but you know that if no parts go into this box, then that part will fit in here. The downside of these is that there's no mounting. So if we look at the Egg Finder's box, all it is a solid cube. The Egg Finder itself does have bolt holes on it, but there's no way to locate those bolt holes in CAD. I thought as a workaround what I could just do is hot glue these down to the sled underneath, wrap a zip tie around them, and call it a day, which might have worked with some other systems, but the Egg Finder and Egg Timer products use voltage regulators that run very hot. So you need to take that into consideration when you're designing parts around them. Of course, it never says that anywhere on the documentation, so it's something you need to find out experimentally by testing your parts before implementing them. So if I was to do this again, I would probably go through and make a couple of revisions to the sled to figure out where the hole positions are on the Egg Finder and Egg Timer. Another approach that you could take is to just print a solid blank slab underneath this component, and then once you have the part aligned on it how you want, you can drill the holes through and just mark them in real life. This is also a good approach to take with custom components that you don't necessarily know the exact dimensions of. So we're definitely going to keep the Egg Finder in there. Let's hide this top bulkhead and everything. And we'll hide the external body tube. So like we said, we don't want pies anymore. Let's just get rid of all of them. And since they're such complex models, it is going to probably take a while for all of this to process. And this one does not want to disappear. There we go. So let's see what we're left with. Down here, we have the power boost. This was used to convert the 3.7 volts from the LiPo up to the 5 volts that the Pies needed to run. Power boost is a simple commercially available option for converting power. Thing is, a lot of avionics already have a built-in voltage regulator that we could just tap off of, and this board is a lot bigger and more complex than the actual voltage regulator itself. We could just get a commercially available step-down voltage regulator that would take up probably 1/8 of the size and it would cost about 1/10 the price. The advantage to these sort of Adafruit breakout boards is that they do have very accurate CAD models with mounting. So if you're doing something very complex with multiple boards, sometimes these are beneficial. For what we're doing though, we really want to save money where possible and simplify the assembly process, so we're going to get rid of that. Now with those other cheaper alternatives for voltage regulation that I mentioned, we run into the same problem that we did with the egg timer products, that there is no easy and accurate dimensioning, especially for mounting holes, if there's even mounting holes on the parts themselves. Many of them are just designed to either be mounted inside of a PCB or floating free in space. So we need to come up with some mounting practices for those. A common one is glue or epoxy, preferably not hot glue since voltage regulators can get very hot. But it is an approach that you can use, something that's going to be very low power consumption. Another approach that I've seen is people will sometimes wrap them in 2 axes with zip ties, and that's a happy medium between the 2 approaches since they are temperature resistant, reversible, and they don't necessarily require accurate dimensions on your part. You just need to generally know the length and width and height of it. Now that we've gotten rid of the recording systems, we can get rid of 2 of the batteries and the transmitter for the video. Another advantage to using these SQ12s that'll help to further simplify the DFA process is that they are completely self-contained units. So we don't need an external memory card, we don't need an external battery, we don't need an external power connection. You just hit the button on the top and they work. This is also good from a standpoint for the launch operations, which is not necessarily DFM or DFA, but something to consider when you're choosing components and building a project. Using those 4 pre-assembled camera units would simplify our launch operations procedures since we now only need to worry about 1 battery instead of 2 to 3. So now we can get rid of this mess of a sled, but first let's pull it out and take a look at the design practices for it. This is another example of a part that was designed to be 3D printed, but it's not great. See, 3D printing is a bit of a double-edged sword when it comes to DFM, in that 3D printing can make pretty much any geometry and it won't complain. You know, if I give square corners to a mill, it won't work. But if I give them to a printer, it will do it. It might not be as good as I want them to be, but it'll definitely do it. That, though, sort of lulls designers into a false sense of security that anything they can make in CAD can be 3D printed, which is not always the case. You need to give special considerations for support material, hole sizing, and other things like inserts. So inserts are a great piece of technology for DFM that I used on this part that I should have used on that other one we saw earlier. When you're trying to thread a bolt into a 3D printed part, unless it's a very large diameter bolt, like over 1 inch, you can't accurately model the threads. So what most people do is they will just undersize the hole slightly, and the first time they drive in the bolt, they will do it with a very high torque Allen key. And what this will do is the bolt will actually cut the threads into the inside of the plastic. This is an okay approach for some applications, but the issue is that it requires a lot of material around the bolt hole that needs to be very well reinforced to take those cutting forces. A better approach would be to use threaded inserts. Threaded inserts are just small pieces of brass that on the outside are a barb or some sort of retaining shape, and the inside is a pre-cut metal thread. What you do is oversize the holes that you want to put your bolts into, and then using a heat gun or soldering iron, you press the metal insert into the hole. The heat will cause the plastic around the insert to melt slightly, and then when it re-solidifies, it'll form around those retaining mechanisms on the outside, holding a well-formed thread inside of your part. The downside is that threaded inserts generally need a very large hole to work. So for instance, this hole here was designed for an M2 or 2mm across bolt. However, the hole itself, I needed to make it, almost 4mm in diameter. So you have to make your part significantly larger, and you also can't make the features around these holes very small, since they need to take on the thermal loading to get that in there. There's also the concern that if you have a part that's too close to the edge, like this one, when you're using a threaded insert, that the heat will deform the shape out here permanently, and the threaded insert won't be in there straight. But if you take all those into consideration, threaded inserts are really a great way to make your 3D printed parts work a lot better. They're just as strong, if not stronger, than the surrounding plastic when it comes to the thread strength. So it gives you just a much easier approach that's much nicer to use than trying to force the threads in yourself. So let's take a look at some other aspects of this. One of the sort of good things about this part is if we move it away from the rocket, you'll be able to see it better. The part is more or less a 2D profile. So what this would mean is that when we print it, all of these walls here are going to be coming straight up out of the bed, so they won't require much support material. Also, when the printer is moving just in the XY space with no support material, you'll generally find that your dimensions are going to be more accurate to what they are in reality. Of course, they're not really accurate. You know, if we had to get a snug fit on a battery, for instance, this is where the 2S LiPos would fit, you could see that I modeled the rectangle to be 35 millimeters across. The LiPos in reality are about 30 to 32 millimeters across, but to make up for the dimensional inaccuracies of the 3D printer, I oversized the holes. There's no set rules when it comes to DFM for oversizing dimensions for 3D printed parts, since every 3D printer will have a slightly different performance profile for how well it can handle accurate geometry. It's best to be familiar with the machines that you're using and then design based on a couple of tests that you can do. When I'm designing to use a new 3D printer, one thing I like to do is just set up a block with a bunch of pins in it, with varying distances between the walls of the pins and the pins themselves. What this allows me to do is very quickly and easily get a feel for how accurate the 3D printer will be when it comes to tight tolerances. For this application, I was 3D printing the parts on just a cheap self-built 3D printer, so everything was awful when it came to dimensioning. This isn't one of the downsides to 3D printing from a dimensioning standpoint for DFM. When you go to have a part manufactured for milling or something, you don't need to worry about compensating for the accuracy of the machine or the dimensioning or anything like that. All of that is handled inside of CAM or the machine's cutter compensation itself. 3D printing, though, is very rudimentary when it is compared to milling or turning, so you need to do a lot of those calculations and adjustments yourself in the CAD. So if this part was to go and get machined, I could make this rectangle the exact size that I want it to, and excluding the fact that it has square corners, they'd be able to match that to whatever dimension I give them, no matter what machine they use. So some bad things about this 3D printed design. Let's start with features like this. 3D printers, when they have free-floating geometry that doesn't have anything immediately below it, need to use support material. Now, support material is not necessarily bad. It will reduce the dimensional accuracy of the part that it is directly supporting, but overall, it's not the end of the world. Something like this, though, is a bit of an issue. If we look head-on at a cylinder that it had to support, the 3D printer does its support by drawing a series of lines up to the feature it needs to support. So we were supporting a rectangle, like this surface up here. Let's say that there was another part up top. It could just draw a series of lines, and that would allow it to bridge the gap between them. So we might see, maybe a little bit of drooping in the part. This is massively exaggerated, but overall it does pretty closely fit what you would expect from a flat part. Maybe touch it with a little bit of sandpaper and you'll be fine. Now when we look at a part that has a curved bottom facing down towards the build plate, the support material will touch there, like we expect it to. And then it'll do one there, yep. And it will do one maybe here. Like that. Now the issue with this is it's only supporting the circle on an infinitely small point of material right there. And then it has all of this arc that it needs to build up in midair before reaching this next part. Not only are we now working against gravity, but the natural constrictive properties of plastic as they cool will cause that edge to curl up. So what may end up happening is this will be closer to a just rough edge, and the material that would have been here starts to get pushed up, and we'll start to see flats on the inside of the hole above it. So when you're designing parts that need to be supported, it's best to give them a very flat, broad base rather than a curve like this. I don't even really know why I went for a curve here. I think it's just because this was a standoff for a bolt. I thought the bolt is round, I'll make the standoff round. So over here, this feature would be much better supported during the printing process. You'd see that it's very flat along the bottom, so when it goes to support it, we'll have much less of a deflection. Also, there's no critical geometry in line with the support material. This hole here, its dimensional accuracy won't be bothered much by any plastic that starts to warp or bend on either side of it. So going around again, you can see the good. It's a very simple 2D profile. Where we need support material, it's a clean cutaway with a large flat base for supporting. The part has a lot of contact area with the base of the printer, which is good for helping it to stop from curling up. These holes on the bottom, depending on which machine you use, might be a bit tricky. 3D printers is a bit of a crapshoot. About half of them, the features that are on the bed, are the most accurate and best features of the print, like with a Prusa i3. But for other printers, like a FlashForge, the features immediately on the bed are the least accurate and the worst made of everything else on the part. So again, it really comes down to knowing what tools you're using when you're doing your DFM. So this part, overall, it could use some improvement, but I would still print this and run it as is today with no major concerns. But we're simplifying, so let's get rid of it. Now, another part to look at that we're not going to change, but it's a good change of pace to go from 3D printing now to traditional machining. Let's take a look at these bulkheads. So since there's going to be charge caps mounted immediately above and below, just above the Avionics Bay, we wanted them to be metal. You could probably get away with a very thick wood with a metal sheet coating on top, but I had aluminum plate stock, so I figured why not. The blanks were very easy to cut in the water jet on campus, since it's a very large, simple radius on the outside, and the inside diameter is very large as well. The water jet is like a laser cutter, but it can cut through metal or pretty much anything else. The downside is that it can't cut precisely on both sides. So if I had this circle, which is a diameter of just under 100 millimeters, and I had the plate that it came out of, the plate probably has a hole that's like 120, 130 millimeters in diameter, and the edge is all jaggedy and broke. Same with the inside hole here. If we took the piece of material that was in here, that was cut out, it probably just looks like a random shard of aluminum rather than a clean cutout that you would see with a laser cutter. So one important thing to note about this is, just to keep everything simple, the thickness of the plate is the nominal size of the stock. So if I change the document settings from millimeters to inches, we can see that this is a 0.186 in CAD. Now that doesn't really match up with any nominal plate thickness. it's possible that I found some odd gauge material, but if I remember correctly, what I actually did was I got some quarter-inch aluminum, and then in the dimensions I marked out that only this dimension was critical, from the base of the lip to the top of the lip, and I didn't really care how much material was above the lip, since that's just sitting in the avionics bay, or in the parachute bay anyway. Just for accuracy's sake, if I was to do this again, I would probably model this to the size that I would want, rather than doing some weird dimensioning on the final print. Now, speaking of dimensioning, when I designed this, I designed it for a nominal tube. So the nominal tube was this one here, which I said had an internal radius of 1.894, and this part had a radius of 1.894, and I called it out as plus or minus 10 thou. Now, there were two main failures there. The first is the tubes themselves have a tolerance of plus or minus about 10 to 20 thou on the inside, depending on where they are in the wrap and which batch they came from. The other issue is that since these parts need to fit together, telling the shop that they can make this part plus 10 thou instead of, say, plus 0 minus 20 meant that they could design this part and machine it to be oversized already. So when I got this part, it didn't fit, wasn't even close. I could have tried to sand down the inside of the tube, but that would have significantly weakened the structural integrity. So instead what I had to do was put this on a lathe and turn this step down a bit more, as well as this to fit inside the parachute bay. The challenge is, how do you hold this part? You have to spin it, there's no identifying marks, this is way too thin to hold on to with a chuck, especially if we needed to machine those features. So I ended up having to squeeze it between two nuts on a piece of all thread that I held in the chuck. This is far from an ideal work holding solution, and it led to a lot of chatter and inaccuracies in these parts. I eventually did get them to fit, but it was a multi-hour process just trying to shave off that little bit of metal. If I was to do it again, I would probably want to do a composite bulkhead, where instead of trying to cut this weird step, which would increase the number of machining steps, so we have to go from the water jet to the lathe and then fit check and back to the lathe, what I would instead do is split it into two parts. So now I can send the shop a thinner piece of stock, and I can tell them I want a circle of this diameter with this hole size, and a circle of this diameter with this hole size. Then I could just bolt the two together with some strong epoxy in the middle, and I have functionally the same bulkhead, but with one fewer machining operations, which saves maybe hours or even days off the turnaround time. And once I did the fit check, so I found something wasn't good, I can get each part individually remade, or just shave them off a bit easier, since we're now just dealing with a single part. I could hold it on the ID with a expansion bore or something, or even just put it on a jig and take it to a belt sander and spin it around to get that final OD into shape. Another good thing to have done would probably be to make a laser cut test fit piece. Plywood is cheap, and we can laser cut this bulkhead in a matter of seconds. So what I should have done is made this bulkhead out of plywood, tried to fit it to the tube, but realized that there's a tolerance stack-up issue, then go back and fix it. The tolerances on these tubes are not great, so while you could try and do a traditional tolerance stack-up study to get everything working properly, I find that it's best just to do a little bit of trial and error and fit it based on the tube that you have. If it's a machined piece like metal, where you have a much more accurate ID and OD control, then I think you can get away with a normal tolerance stack-up, which, if you're not familiar, refers to the idea of the nominal for this fits the nominal of this, but then how do I make it that through all the possible ranges of tolerances, it will still work? So with two simple parts like this, the approach that you would probably take is tolerance this part that the diameter can be X plus maybe 5 thou, 10 thou, but minus 0. The machining parameters for this say that we cannot make that any smaller. On the flip side, this part we would say it can be whatever the diameter is plus 0, i.e. it can't be any bigger, and minus whatever tolerance we want to give it. 5, 10 is usually common. Now the downside to that is, nominal fit to nominal fit. We know it'll be a nice, snug, perfect fit every time. But at the absolute edge of our tolerances, this one could be 10 thou undersized, and this one could be 10 thou oversized, so we'd end up with 20 thou of slop in the middle there. So it's all stuff that you need to balance when you're designing and choosing your manufacturing practice. Or, for one-off things like rockets, the approach of getting close to nominal and then reworking to fit, like I said, sanding or returning it, is good enough sometimes. So another good thing actually on the bulkhead is if we look, this rocket has 2 identical Avionics Bay bulkheads. So this goes back to the DFM idea that programming and setting up a part is about 75% of the work. So if possible, you want to use duplicates of the same part wherever you can. So in theory, I could have made a more optimized bulkhead for the top than the bottom, but by using the same design on both, it saved a lot of machining time. For example of what I could do to optimize it is I could have had the shop pre-drill the holes in this top bulkhead that I would need to pass through wires or to connect up the charge canisters. But that's all stuff that I could do as a secondary operation pretty easily. So now let's hide those. The all-thread through the center of the Avionics Bay is a classic DFM practice and a DFA practice. It is simple, reliable, and it will take care of all the structural loading of the bay, so you don't need to worry about that when you're designing. So I would definitely still do that. And the nuts that I used on the all-thread were all Nylox, which means that they have a nylon gasket inside that will hug the threads a lot tighter as it's spinning. What's nice about this is that they won't freely rotate and move along the threaded rod as they're vibrated. The downside is that they take a lot more force to apply. So these are good for applications like rocketry, where the flight forces sometimes can shake and vibrate nuts and bolts to the point where they'll start to unthread each other. It's not as good or as foolproof as something like thread wires or thread lock, though. So it's a good middle of the road between easy to use and reversible, as well as giving you some resistance against the vibration. So let's hide that. Now, all that we're left with in here is our egg timer quark, our battery, our tracker, and our switch. And on the switch, you can see actually, I went through and did the work of locating the mounting holes inside of the keep out box. So now I can use that and mount it with screws. I'll probably go back through and locate the screw holes on all the other parts as well, so that I can mount these all with bolts rather than glue. Before we go into designing the internal of this bay, though, I do want to talk about the outside, because if you notice, there is something special about its design. So if I open that, oh, there we go. So again, this is translucent just for demonstrations. The actual part is just a blue tube coupler. So in fact, I could switch that back right now just by doing that, and then by doing let's make it blue. Oh, wait a minute, that's right. So sometimes in some of my older designs, what I would do is I would change the physical material of a part to something clear like acrylic to get a better view inside of it. And that's something that I've seen a lot of other people do on their rockets and their designs in Fusion in general. But there's a really good tool that not a lot of people know about, and it surprises me. If you go in your browser and right-click on a component, you can change its opacity, which will then let you see through it a lot easier. So, Avionics coupler, I don't really care about what it looks like from the outside. So I could make it clear. I can even hide it altogether, but maybe I still wanted a general idea of where it is, so I can turn the opacity down to 50, 30% maybe. Another thing that's useful in this menu that a lot of people don't know about is the selectable unselectable. So let's say that I'm doing work on the coupler, care about this outside body tube. Maybe I want to work underneath it, but for some reason I can't turn it off. And maybe I want to see what's underneath it and then modify what's underneath it. I could set it to unselectable, which then shows a little icon in the browser. And now I can select and do work underneath this part. And it's like it's not even there. See, I can't select any features on it. I can select the features underneath it and around it, but it doesn't matter. And then you can just turn selectable, unselectable back on whenever you want. You can also apply that to entire subassemblies or component groups. So it's good for if you want to work on only one aspect of your rocket at a time. So, maybe if I want to work on the Avionics Bay, I could turn off the booster, and then the sustainer I could just set to unselectable and increase the opacity. So I can still get an idea of where it is as I'm putting stuff together. So looking at this part, this is a surprisingly deceptive piece to manufacture. So normally the Avionics Bay on something like Charm, it's pretty straightforward. All it is the coupler tube cut to length, nice and simple. A body tube cut to length, nice and simple. The challenge is we wanted to put a lot of cameras in this. So I needed to put these 4 holes all the way around the Avionics Bay. Now, when you need to put holes in the Avionics Bay for things like venting, usually that's done by just drilling a small hole somewhere. It doesn't really matter where it is, so long as it's not right on top of your barometric sensors. For these camera holes, though, I needed to make sure that the holes on the outside of the bay matched up with the positioning of the cameras inside. So these all needed to be done quite accurately. The challenge is, how do you actually put them in there, The first thing I tried was using the laser cutter and holding the tube, laser cutting it, rotating it 90 degrees, laser cutting again, etc., etc. The challenge is with that is twofold. One, you can't laser cut blue tube, not very well at least. It likes to more burn than actually cut. The other downside is I didn't use a very good jig as I was rotating, and at the time we didn't have the 4th axis for the laser cutter in the construct. So what ended up happening is this hole to this hole was maybe 86 degrees, then this hole to this hole was maybe 110 degrees, and this hole to this hole was, maybe 80-something degrees. So when I put everything together, some of the cameras were dead on center, and some of the cameras were sort of off to the side, a little bit weird. You could try and drill them by hand. It's very tricky, obviously. There is some trickery you could do with string and some math about the diameter of this tube to very accurately mark out the center points of all these holes. So that would be an option. Another very cheap and easy and simple way to do this would be, instead of trying to cut this part out of blue tube and then putting holes in it, I could just 3D print it. If I 3D print this part and slide it onto a coupler and glue it in place, without drilling any holes in the coupler, I now have a jig and a final part that will tell me exactly where those holes need to be drilled. Then I can just match up a drill bit to that 3D printed part and drill a hole straight through the coupler. I had also tried to manufacture lenses to increase the altitude of this rocket by reducing the drag around these holes. What I had tried to do was take a acrylic tube and then make a piece of acrylic that would perfectly fit this. Since it's the same diameter tube and the same thickness, it would just slot right in. Just like with the nose cone bulkhead, though, I ran into a lot of issues that things don't really go as well as they look in CAD. The parts would just fall right through. I ended up getting glue on them. It just ended up being a mess. So if you do end up needing to put some sort of like sunken part into the side of the rocket for aerodynamic purposes, try and make them as big as possible to work with. And I could have also saved myself a lot of time and hassle by just taking this hole in the coupler tube and somehow making it slightly smaller than the hole of the body tube itself. Now the lens could just sit flat on that lip there, and I wouldn't have to worry about alignment or anything. The downside, of course, is now I need to figure out a way to manufacture this diameter hole down to a flange, and then this diameter hole all the way through, which can be a bit tricky at times. So now that we got that out of the way, that's pretty much all there is to the Avionics Bay. Obviously, there's a lot of improvement that can be done there, and I'm definitely going to go through and change a lot of stuff around in a future video that we can review some new practices and techniques for designing for 3D printing specifically. For now, though, let's move on to the booster. So the booster is your run-of-the-mill, pretty standard booster. We have a center motor retainer tube. We have a couple of wooden centering rings down the length. Those are just laser cut, and if they're a bit bent or misaligned, nobody really cares because the tube in the center ensures the motor still fits either way. Cicerone is really great, and so is Aerotech with providing accurate CAD models of their motors. So designing is super easy. Let's go ahead and hide the motor casing. There we go. So down here in the booster and a lot of rocketry boosters, it's very much a permanent assembly. You don't see much in the way of nuts and bolts down here since you have very little space and a lot of forces. Generally just slathering everything in epoxy, calling it a day is a much easier approach. So you see this center tube can never come out. It's glued in there. All that's glued. The fins, they're on a tab. They're all glued. The boat tail. At first, I had a boat tail. Here we go. Where is it? There we go. So I hide the new boat tail. And that and that. There we go. So I originally had a boat tail that was actually bolted on that could double as the motor retainer. Let's take a look at this part. Now, the obvious issue with this part is that it is right below the motor, so it needs to be able to withstand the exhaust heat and pressure, as well as being strong enough to retain the motor during the shock forces of deployment. Now, some people, and I've done a lot of research now, it seems that you can get away with a high-strength 3D printed part for this application. But I had it in my mind that plastic equals bad, metal equals good, which is a mindset that a lot of designers will fall into. So I made the poor folks in the shop machine this abomination of a part out of a solid billet of aluminum. And I don't know how long it took them. It was a week between when I submitted and picked up the part, but I feel awful for the kind of work they had to go through to get this part. If you just look at it, I started with a solid billet. So they had to go in and they had to core out all of this material just one pass at a time with a drill and then increasingly finer and deeper boring bars to get the final part. Then I didn't really give them anywhere to hold on to. All you have are these very thin flat faces, and even then they have cuts in them, so you can't really clamp onto them very tightly. So they had to do this entire long stick-out part just by using whatever very light depth-to-cut tools they had while holding on all the way back here. Then on top of that, I gave them these sections here that were for the clearance on the fins, which needed to be a square base to fit the fin. which, obviously it's impossible to do. I don't even know how they did it. I think they went in with a file and actually filed it flat. If I wanted to do them a favor with this part, what I would have done is extended the slot down so it's beyond the base of the fin, and then round it out so they can just go in from the side with an end mill. It's also a challenge that these slots need to be located 90 degrees around the top of the part. So they had to locate this part centrally around a fourth axis, then rotate it and machine each of those features in, along with these bolt holes that need to be spaced evenly around the outside and then threaded as well. So overall, this is a terrible, terrible part, and I feel bad for the fact that I forced people to manufacture this. Let's take a look at the new approach instead. So the new boat tail I settled on was 3D printed. Now, this one, I don't have it retaining the motor. So I had to go for an alternative motor retention practice, which is not the end of the world. The benefit is this part I can make in 12 hours on any 3D printer, and it works just fine. Had to print it out of PET to get the strength and the heat resistance I needed, but overall it's a much simpler part. I could lay this flat face down on the bed. There'd be a tiny bit of support material on this lip here and on the base of the fin slots, but other than that, it was all good. Challenge is, just like with the bulkheads for the parachute bay, I didn't really take into account the tolerancing of the tube. So what ended up happening was this was way too big and it started to splay the tube base outwards. So I had to go in and file it down, and if you go and look at this rocket today in the College of Engineering, the base of it is really ugly. All that filing and sanding and trying to get this part to fit rather than just remaking the part, admitting defeat, I ended up with just a mess of glue and epoxy and filler, and it just doesn't look good. If I had it my way, I would honestly just completely redo the booster. Not even from a DFMA standpoint, but just from a build quality standpoint. There's so many small tweaks I can make that would make the assembly process much cleaner and easier, as well as just making the entire thing look better at the end of the day, which is really important if you think about it. So moving on, one of the things I'm really proud about is this fin retention. Let me hide the body tube, which by the way is just a tube. Cut it to length, can't get much simpler than that. We'll hide the centering rings, we'll hide the motor mount tube, and we'll keep the boat tail. So this was a great design, and I love it, and I'm going to use it on a lot of my future rockets as well. So the fins on this rocket are not only very long and very thin, but they're also swept. So I already have most things working against me when it comes to a fin flutter loading case. So just doing a normal through tube tab with these fins would not have worked. So I needed a way to solidly secure the fins inside the body tube, but at the same time it had to be a stack of parts that I could press in from the back, since the motor mount tube would already be centrally mounted inside the airframe at this point. So what I settled on was a series of 3D printed and laser cut wood parts. These 3 wood parts here are just a centering ring with slots cut for the fins. And again, to the point of reusing parts, they're all identical. That would clamp on around the fin with friction and a little bit of epoxy. Then, on the top and bottom of this stack, I had 3D printed parts with a flange that would retain the front and back of the fin. The back of the fin is also held by this flange of the boat tail. So we have a lot of clamping force using a lot of very simple parts, very easy to manufacture parts, that helped us to get better performance out of these fins without sacrificing altitude. Now the fins themselves, if I turn off analysis, you can't see under the paint job, but these are carbon fiber fins. Carbon fiber is a common material for fins since, especially at higher flight speeds, you're going to have so much flutter that anything else will just shred. Now, manufacturing carbon fiber at RIT is a little bit tricky. It's incredibly easy to cut it on a bandsaw, and there are bandsaws especially made at RIT for cutting carbon fiber. But any machining is next to impossible. It takes so much setup time, safety precautions, specialized tooling. It's just not worth it. So, really, just keeping to simple straight lines that you can cut by hand on a bandsaw is the best approach for the fins. What I did to get these fins cut out is I had my plate of carbon fiber that was, I think, 12 inch by 12 inch, and I printed out a 1:1 scale drawing of all of my fins, and then I glued them down on top of the carbon fiber. Then when I was at the bandsaw, I could just cut along the lines on the paper, and it would cut the carbon fiber underneath as well. If I had to do it again, what I might do is cut the carbon fiber into 4 quarters, secure all those 4 together with the paper on top, and cut all 4 fins at once. But I'm not really sure if the bandsaw can handle that thick of a cut at once. The upside is that it would cut the machining time down by a factor of 4, and all the fins would be identical to each other. So you can see here, this is a very simple to cut shape. It's all straight lines, and you can even get these sharp internal corners by just going in from both sides of the bandsaw. So the fins are nice and simple. Those turned out pretty well. Securing the fins, I do wish I left myself more tolerance between all these parts for the glue. These are a very snug fit, and the downside is most glue has something called I think it's referred to as a meniscus diameter. And what that refers to is, epoxies can flow freely like a liquid, but they can't flow through, obviously, a sealed surface. It might need a 10 thou gap between the two, maybe a 20 thou, 30 thou, 40 thou gap, for that epoxy to be able to freely flow in and create a solid bond. There are even some specialized epoxies and glues, like I think it's Loctite 504, is designed that it can go between parts that are only a thou or 5/10,000ths of an inch apart and get a good bond between them. Now, of course, that stuff is very expensive. It's best to just use your traditional 2-part epoxy and take the hit of having to properly tolerance everything. So, all in all, it's not a completely failed design, but there is definitely a lot of things that I would fix or do differently going forward. I might even go as far as to redo certain parts of this rocket before it actually flies. Like we said, that whole Avionics Bay, I can massively improve. I can do some improvements to the booster down below as well. But for the most part, this is a rocket and a design that I am happy with, and it will serve the purpose that I need it to. Make sure to stay tuned for future videos where we will go through how to actually design all the internal parts for this, as well as some more example design parts for how we can further improve this rocket. Hopefully, you guys learned some interesting new techniques from DFMA today, and I hope that you will all in the future go through your past designs and see how you can improve or how you even have improved as a designer. Before we finish up today, are there any questions from the chat related to DFMA? There's a bit of a stream delay, so there's going to be a good minute or so before we get any of those questions. Just stick tight. In the meantime, while we're waiting for those questions, I could talk a bit about some future live trainings we're going to do. We're going to go through a lot more of my other designs, both rocketry and non-rocketry, and continue to rip them apart piece by piece. And, it sounds harsh, it sounds funny, roasting yourself about your designs, but it is really a great practice, and I do strongly suggest that everyone does it, no matter how insignificant of a design. Even that M4 block that I showed you earlier for holding a nut, in a year I can come back to this design and there's probably a few things that I could find that I could better optimize about this. Even now I know that I can increase these radii to make it easier to hold when I'm actually installing it. I can functionally drive this radius, so I only need one file for every body tube shape. And I can play with the tolerancing back here to make this nut a press fit instead of having to epoxy it in. So you see, even something very simple like this, there's so much that you can go back and learn and do and improve later on. So it doesn't look like there's any questions, so we're going to call it there for today. Thank you all for joining me, and I hope to see you all next time.